Alrighty, good morning. Welcome back to Calc 1 Honors. Sorry about that delay. I'm having some issue with the single sign-in for Zoom. I keep getting booted out. Hopefully we've got it fixed and there will not be any interruptions today. Today is going to be our second day talking about USUB. Our second whole day focused on this because I really want to make sure everybody gets a strong and confident handle on this topic because it is just that important. You may remember that cutesy little flowchart from XKCD I shared with you guys a couple classes ago about integration. You'll notice that the first stop in that flowchart was substitution, right? Substitution, integration by parts. Probably the two most important methods for evaluating integrals, two hugely important methods for proving theorems, just really big stuff. Last time, we looked at a handful of integrals where the differential term was constant. Those were easy. We looked at a handful of integrals where the differential term was beautifully and completely soaked up or canceled perfectly with the remaining pieces of the integrand after you made your substitution. Those are not bad. You can be a little bit careful, but not bad. Today, we're going to look at a few slightly more challenging USUB problems. So it may be a slightly quick day, that's okay. We're coming to the end of the semester. We're slowing down because again, I really want to make sure that you guys are masters of this stuff moving into Calc 2 because it is just that important. So let's go ahead and get started. This is MAC2311 section OH1. It is a lecture, and today is the 7th of April, 2021. Today, we're going to do some slightly harder substitution integrals. And I'm going to begin with a duo of problems. They're kind of connected to one another. And the first one is about at the level of the problems we were doing on Monday. So just to make sure everybody is on the same page. Let's dive in. So today is pretty much all examples. I'd like to begin by evaluating the indefinite integral of x times the square root of x squared plus 1 dx. I do want lots of interaction today. The goal is to kind of get a feel for where you guys are at with this material to help me pace out the remainder of the term. So I'll ask you, what should I do? What is a good first step here? What are we going to do with this thing? Yeah, feel free to type in chat or you can hold space to talk. Yeah, Kevin and Katie, both correct. We need to pick what we're going to substitute for, right? I've said it before, I'll say it again. The square root of x squared plus 1 is super duper not ever equal to x plus 1 itself, right? We cannot distribute this square root because powers never distribute over addition or subtraction. So we can't jump in and hope to simplify algebraically. That's not an option. So instead, we need to do a u substitution. And Kevin and Katie are on the right track there. We got to pick u. And Katie's choice of u is a good one. The real challenge in this integral is coming from the square root. Because we cannot distribute that power, I really need like one thing under this square root, not two separate terms. I need like a single term under here. So that I can then apply my power rule. So if we make the substitution, u equals x squared plus 1, we will do precisely that. We will replace this two-term expression with a single term, just u under the root. What do I do now? Now that I've chosen u, what do we do after that?
Right.
Very good. We need our differential. We need the du. So what is the differential du here?
2x.
Certainly there's a 2x. What else? So remember, this isn't just u primed, the derivative, it's the differential du. So du here is 2x
and dx.
dx. Very good. And that's important because the whole idea with the differential is that I'm going to replace this dx by something. And the thing I replace it by is determined by this. So if we don't write the dx here, it's easy to get quite lost. All right, now I write down what my integral appears to become. I'll leave the x here for the moment. I know that the square root of x squared plus 1, that's going to be the square root of u. And then I have this dx chilling over here. All these things are being multiplied. I want to say that this is not really a meaningful statement. Think of it as like a mnemonic. It's something that helps you get to the meaningful statement, but I could not integrate at this stage. We cannot have a mixture of x's and u's. We need to get rid of all the old variable stuff, including this and this, before we can do any antiderivative work. So what do I do now? I've replaced the piece with u that I intend to substitute for. That's good. After you do that, we need to replace the differential by its equivalent expression. So we come back over here, and I solve this for dx. I do that by dividing both sides by 2x. So I get 1 over 2x du is equal to dx. Which means that my integral here is going to become, and I'll continue writing all these terms, x square root of u times 1 over 2x du, right? This dx is 1 over 2x du. That's what we found here. And lucky us, this x and this x cancel. So I get integral square root of u times 1/2 times du. And at this stage, the substitution is done. Right? It wasn't done here because I hadn't replaced this dx and I hadn't gotten rid of this x. I need all the x's to go away before I can really say I've finished with this substitution. What would be my next step from here?
You would want to put original what u was equal to before, so that'd be x squared plus 1.
We're not ready for that. So in an indefinite integral, we will in the end plug back in for u. But the whole point of the substitution is to move the integral away from x's into u's.
Yeah,
so
you want
our antiderivative first. So I would say let's pop that 1/2 out, and then the square root of u is u to the 1/2 du. So we need to do our antiderivative before we plug back in. And that's an important thing. I do see that a lot, especially in the first week or so of Calc 2. The swapping back to the original variable, we only do that in indefinite integrals, and we only do it at the very, very end. It's our very last step. The miracle of this substitution is that I've gone from an integral I don't know how to do to an integral that I do know how to do. So now that we've rewritten this after our substitution as a nice simple integral, we do the integral. We take the antiderivative. So Julio is correct in saying we're going to go back. We're not quite ready for that. Before we do that, what do we do with this piece?
we would take the antiderivative and then the integral and the differential.
Yeah, perfect. So we need to take an antiderivative, and then when we do that, this integral and differential will go away. What is the antiderivative for u to the 1/2? This 1/2 out front comes along for the ride. And then an antiderivative for u to the 1/2, what does that look like?
We have u to the 3/2 divided by 3/2.
Very good. Yeah. So I increase the power here by 1, That'll give me u to the 3/2. And then I divide by that new power. Now, instead of writing this as u to the 3/2 divided by 3/2, we know that when we divide by 3/2, we're going to have to flip and multiply. So I'll go ahead and do that at this step. So an antiderivative for u to the 1/2 is 2/3 u to the 3/2. And it's at this stage where we also start writing our plus c. So once you get down to an integral you know how to do, you take your antiderivative and you slap on your plus c. Taking the antiderivative makes the integral and du go away. And because this is an indefinite integral, no bounds, we write a plus c at the end. Now I can cancel these 2's. And I get 1/3 u to the 3/2 plus c. Am I done?
You have to do the last step where you
Yeah, so our very last step is to swap back in for u. Because it's an indefinite integral, look, the original question was like, this is basically asking, what is the most general antiderivative for x times the square root of x squared plus 1? If I didn't show you the in-between steps and I said, this is the answer, you'd be like, what the hell are you even talking about? I don't know what u is. So we need to go back and plug in for u. And u was x squared plus 1, so this is going to be 1/3 parentheses x squared plus 1 to the 3/2 plus c. And just like we couldn't distribute the square root, we can't distribute this power. I cannot give this power to these pieces separately. So this would be our final answer. If you really want to, this answer can be rewritten a couple different ways. We could write this as 1/3 times the square root of parentheses x squared plus 1 cubed plus c. Or you could transpose those powers. You could write this as 1/3 times the square root of x squared plus 1 all cubed plus c. Either of these would be acceptable. But because there's no way to distribute the square root, there's no way to distribute this power. In this expression, you could FOIL out the x squared plus 1, right? You could write it as x squared plus 1 times x squared plus 1 times x squared plus 1 and then distribute everything. But there's really no sense in doing that. So 99.999% of the time, the right way to leave it is just like this. This is the nice answer. All right, any questions on this fella? Okay, so here we had an example where we made a little substitution. Our differential terms canceled really nicely, right? All of the x's canceled without us doing anything special as soon as we plugged in for dx. Not every substitution problem is that nice. If you're lucky, all of those terms will cancel, and at most you'll have a constant multiple to deal with. But if you're less lucky, there will be other instances of that old variable still floating around. So for our kind of gentlest example of that sort, I'd like to just take the square away from the inside. I'd like to look at this guy. So again, it's an indefinite integral. Again, I have a square root of a two-term expression and then an x out front. How do I get started here?
evaluate where you want to substitute u for.
Yeah, we got to pick our substitution. And again, because the square root is the thing that's kind of making life hard, the fact that I have two different terms under this root, I'd like to substitute for x plus 1. That's perfect. So we're going to substitute u equals x plus 1. And then after we pick our substitution, we immediately need to calculate the differential du. What is du here?
It's just dx.
Yeah, the derivative of x plus 1 is just 1. So du is equal to 1 dx. And we just write that as du equals dx. Again, no bounds to worry about. It's an indefinite integral. So that's our whole little substitution box. And if I go plugging in the natural things here, we will get this square root is going to be the square root of u. Dx and du are equal to each other. So I can write du for dx, but I still have an x out front here. Of course, these are all multiplied. And this leaves us with a problem. Remember what we said, we really can't do jack shit until every piece of that integral is rewritten in terms of the new variable. If I have any x's or dx's floating around, I can't do anything until I get rid of that shit. How do I get rid of the x? This is sort of the new thing for today, so take a second to think about it.
I mean, maybe you could solve for it. Like u equals x plus 1, so maybe x equals u minus 1.
That's perfect. Did everybody hear what Julio said? That's perfect. So the magic here, I've got an x left over, and that's kind of an issue. I need to get rid of it. I don't want to make it poof disappear. I want to rewrite it in terms of this new variable. So if I'm only allowed to have u stuff in my new integral, no x stuff, any leftover x stuff needs to be re-expressed in terms of the new variable u, or whatever you choose to call your new variable. We've been calling it u. So if u is equal to x plus 1, that's equivalent to saying u minus 1 is equal to x. Which means this x here, which is a single term multiplying the square root of u, is equal to u minus 1. So I replace it by parentheses u minus 1. And now every piece of my integrand is written in terms of the new variable. So the substitution is complete at this step. Not before it. We couldn't possibly take the integral here for lots of reasons. You can't just integrate two pieces that are being multiplied. That shit never works. Just like you can't differentiate two pieces that are being multiplied without the product rule. You can't do that, with an antiderivative either. And more importantly, you have a mixture of x's here. This du at the end, people think of it as telling you the variable with which, or with respect to which you are integrating. I can't integrate x du. We don't know how to make sense of that. And I certainly can't integrate x times the square root of u du. That shit just straight up doesn't make sense. But this is just a function of u, and I want to integrate it with respect to the variable u. This does make sense. So any steps that are in between here, we have to navigate our way through to get the integral into all the new variable, right? None of the old variable floating around. Okay, so from here, this is a problem I could have given you last week, right? What do I do to solve this?
We would have to the u minus 1 to the square root of u. If I rewrite square root
Yeah,
of u.
good. We'll distribute. We'll distribute. So this is going to be the integral of u times the square root of u minus 1 times the square root of u, which is just the square root of u du. And pay attention to the notation here. Anytime you have an integral with more than one term inside, you should always put the whole thing in parentheses, because this du at the end, you think about it, really is multiplying everything. And if you wanted to make another substitution or do something else like that down the line, it's crucial that you think of this du as multiplying this whole thing. WebAssign fucks this up. They don't always put these parentheses here, but you really do want them. So use good notation. Always put your integrand in parentheses. All right, from here, u times the square root of u, this is u to the 1 times u to the 1/2 minus u to the 1/2 du. I can just do some algebra. U to the 1 times u to the 1/2 is u to the 3/2. So the thing I need to integrate is u to the 3/2 minus u to the 1/2 du. Just algebra, nothing crazy. Now I'm ready for an antiderivative. All right, now that my integrand is just a power function plus or minus another power function, I know how to take antiderivatives of these. I can take the antiderivative of each piece separately. We can split it up. This is the integral of u to the 3/2 du minus the integral of u to the 1/2 du. Again, you see the du kind of behaving like multiplication. It gets distributed. What is this first piece? The integral of u to the 3/2 du. Very good. So when you add 1 to that power, 3/2 becomes 5/2. When you divide by 5/2, that's the same as multiplying by 2/5. So I have 2/5 u to the 5/2. I could write a little plus C1 here if I wanted, but I'll just write a single constant at the end, since we know we're going to group those and just write one constant at the end. Following the same rule, the second piece become u to the 3/2 divided by 3/2. That's 2/3 u to the 3/2. And then, like we said, plus c goes at the end. Finally, because it is an indefinite integral, right? I don't have any bounds, so I'm not plugging in numbers or anything like that. That's why we have a plus c. It also means we have to go back and plug in for u. So this is 2/5 parentheses x plus 1 to the 5/2 minus 2/3 parentheses x plus 1 to the 3/2 plus a constant. And again, these powers don't distribute. I can't give them to these pieces individually. I just have to leave it like this. I could write this as x plus 1 to the 5, all under a square root, and x plus 1 parentheses to the 3, all under a square root, but that's uglier than this. Let's just leave it like this. This is a classic problem. I'll tell you, when I first started teaching Calc 2 here at Santa Fe, and all through my teaching career before that at UF and UCF, I would put a problem like this on my first Calc 2 exam. And 9 times out of 10, I would catch out about half the class, just not knowing what to do with this piece. Sometimes people would pop it out of the integral and treat it like a constant. Other times they would try to integrate these things separately. It's a very common thing. I don't do that on my Calc 2 exams in Santa Fe anymore, because I feel like it's a little bit underhanded. You know, most of our Calc 2 students here aren't prepared for that, because most of our Calc 1 classes, unlike yours, do not handle U sub thoroughly. But I'll tell you this, my wife took Calc 2 with Professor Nieves here at Santa Fe, and he put this exact fucking problem on their first test. And again, it caught out most of the class. I stood outside in the parking lot watching people come out, just listening to kids talk. And the most complained about problem that day was actually this one. So how do you handle the leftover pieces after you've done all the obvious stuff with your substitution? You go back to your substitution equation where you chose u, you solve it for x, and then you plug that back into whatever leftover pieces there are. What order should you put the pieces in? Well, you're going to pick your substitution. So right away, you should put that in. Then you should put in your differential. And sometimes things will cancel, sometimes they won't. Sometimes they'll cancel partially, sometimes they'll cancel completely. But your first step after choosing your substitution and calculating your differential, changing bounds if you need to, is to plug in the obvious pieces that you're going to call u, plug in for your differential, and then see what's left over. If there's stuff left over that doesn't cancel, like here, this x, then you need to go back and solve your substitution for x, and that will tell you what to do with those leftover pieces. Whatever they are, they're going to just be in terms of x, so you'll always be able to do this. Let's try a slightly harder one. This time I'm going to do a definite integral. We'll do the integral from 0 to 1 of x to the 5th times the square root of x squared plus 1 dx. Sorry, it's nothing. All right. Ideas here. What should we do?
It substitute un for x squared plus 1.
Very good. All right, definitely going to do some u sub. And again, it's the thing under the square root that's giving us the headache. I want that to become a single term. So I'm going to substitute for that. You see patterns here, right? This is something we do a lot. What do we do next?
Oh, we just find a differential du.
Good.
It should be
Very good. So what is du here?
2x times dx.
Excellent. And I know it's not a habit we get into right away, but I'm glad to hear it in Julio's response there. And I would like to know that it's in all of our brains. Never skip writing this thing. This thing is important. If you skip writing this thing, it's possible to get lost in the problem. So always du is whatever the derivative times dx, or whatever your variable is here. This one is a definite integral. So in addition to these things, we also need to change our bounds. And again, I don't care what your high school or previous calc professors have said. You need to change the bounds, not optional. So when x is equal to 0, my old lower bound was 0. That's an x value. Remember, this is like the area under this curve from x equals 0 to x equals 1. So when x is equal to 0, my old bound, u, my new lower bound, is equal to what?
1.
Yeah, very good, right? We plug 0 in here. This is the Bible to go back and forth from x's to u's. So when x is equal to 0, u is equal to 0 squared plus 1, which is 1. And when x is equal to my old upper bound, which was 1, u will be equal to 1 squared plus 1, which on a good day is 2. So here's all the stuff I need for my little u sub. Now we start rewriting our integral. The integral from 0 to 1 becomes the integral from 1 to 2. This x to the 5th, I don't quite know what to do with him yet. I'm just going to let him hang out. The square root of x squared plus 1 becomes the square root of u. And then I'll write the dx here for now because dx and du are not equal. I will plug that in a separate step. So first, update your integral, plug in the u where you chose to substitute. Now you look at what all is left over. And at this stage, sometimes you'll need to strategize a little bit. You need to think. But if you're looking for a nice mechanical way to do this, the most mechanical, like surefire, turn the crank, don't have to think way to do it, come back here and solve this for dx. So since du is equal to 2x dx, we learn that 1 over 2x du is equal to dx. So now I plug that in. I leave everything else the same, just in place of dx, I'm going to write 1 over 2x du. I'll have integral 1 to 2, x to the 5, square root of u, all of these are multiplied, right? Times 1 over 2x times du. A few things happen here. Since all of these things are being multiplied, this x down here can talk to this guy up here. He's going to make this power a 4. And also, I've got a factor of 1/2 here that can come out. So I have equals 1/2 integral 1 to 2. There's still an x here. It's just x to the 4 now. So that's a problem. And then I have square root of u du. All right. What can I do with this?
You're gonna have to get rid of the x to the 4, like right in terms of u.
Very good. All right. So the challenge here is that I still have x's and u's mixed together. This is now a u integral with u bounds. I've got the square root of u and du. So this motherfucker right here is a problem. The magic tool for going back and forth from x's and u's is your substitution. Since u is equal to x squared plus 1, we know that u minus 1 is equal to x squared. And now there's two ways to kind of proceed from here. You could take the square root on both sides, and maybe I'll do it like that just to try and get maximum clarity. Or I could recognize that the piece I'm trying to replace is x to the 4. So I could square both sides. But let me just try to keep this simple. So if I solve this for x, I would get the square root of u minus 1 is equal to x. I'm ignoring the plus and minus here. Technically, there should be a plus and minus there. Which means that my integral, I now have 1/2 integral 1 to 2 square root of u minus 1 to the 4 times the square root of u du. You see what happened there? So I just solved my substitution for x. And then here where I had x to the 4, I plugged that in. I now have this to the 4 because x is equal to u minus square root u minus 1. When you raise the square root of u minus 1 to the 4th power, what do you get? Very good, u minus 1 squared, right? Remember, this square root is a 1/2 power. So this is u minus 1 quantity squared times the square root of u times du. And again, now this is a problem I could have given you last week. So at this stage, the substitution is done. this step, but not before. Right, before this step, anywhere up here, I guess really, I could say this step. We had to get rid of this x. Couldn't continue, couldn't proceed, couldn't do any sort of integration antiderivative work without getting rid of that. To solve this, we FOIL this out, distribute this, take our antiderivative and evaluate between bounds. So let's go ahead and do the algebra. I get 1/2 integral 1 to 2 u squared minus 2u plus 1 times u to the 1/2 du. This is pen gonna die. Du. Then I'll distribute my u to the 1/2. U squared times u to the 1/2 is u to the 5/2 minus 2u times u to the 1/2 is minus 2u to the 3/2. And then plus 1 times u to the 1/2 is just u to the 1/2. Now we're ready for antiderivatives. When we take the antiderivative, the integral symbol and the du go away. Adding 1 to 5/2 gives 7/2. This will be 2/7 u to the 7/2 minus adding 1 to 3/2 gives 5/2. So this will be 4/5 u to the 5/2. And this will become 2/3 u to the 3/2. And everything gets evaluated from 1 to 2. The 4 in this 4/5 is coming from the 2/5 and this 2. Before I evaluate, a nice fact is that these evaluation brackets behave like parentheses. You can distribute constants over them. So I'll go ahead and distribute this 1/2. That'll knock these 2's down. This will become 1/7 u to the 7/2 minus 2/5 u to the 5/2 plus 1/3 u to the 3/2 evaluated from 1 to 2. And I can go ahead and plug in the 2 and the 1. So when I plug in the 2, I'll get 2 to the 7/2 over 7 minus 2 times 2 to the 5/2 over 5 plus 2 to the 3/2 over 3. This is what I get by plugging in the 2 for u. We don't go back to x's, right? This is a big difference between definite and indefinite integrals. At no point do we plug back in the x's here. We just plug in these bounds. And then I'll subtract what I get when I plug in my lower bound. So all the signs are going to flip. When you plug in 1, all of these u's are just 1. So this will be minus 1/7 plus 2/5 minus 1/3. And I would leave it here. You can combine some of these terms if you want, but I don't think it's really worth it. These first 2 terms can be combined pretty easily, and all 3 of these lingering terms can be combined pretty easily, but I would just leave it like it is. Questions on this one?
For the notation, wouldn't the second part, like the 1/7 plus 2/5 minus 1/3, have to be like separated? Oh, you already accounted for that. Never mind.
Yeah, I like distributed the negative, so I just flipped the sign on each of them. But if we were being careful, I would have like this in parentheses minus, and then this with all the signs as they originally were. But kind of getting a little bit quick at distributing those negatives, there's no harm in that as long as we don't lose clarity, as long as it's clear what steps you're doing. So that's kind of an important step. We had an x to the 5, right? Integral x to the 5 root u dx. And when I swapped in the dx for its du counterpart, so because du is 2x dx, if I solve this for dx, I get dx equals 1 over 2x du. So this piece right here became 1 over 2x du. This x right here canceled one of the x's from x to the 5, and that knocked that power down to x to the 4. Yeah, it's a sneaky thing, but it's definitely important here. In fact, if not for that, we would have been in some real trouble. The fact that this power is even is kind of important for getting rid of the square root of this step. All right, I'll zoom out here and leave just a minute or two for people who want to polish notes, make sure everything is where it should be. Maybe I'll leave this page for 10 seconds, and then we'll bump up for about 10 seconds. I have two other problems that I really want to share with you guys today. Here's the second half of that last guy. Two other problems that I really want to share with you guys today. And they're both integrals of trig functions. When we were writing out that large table of antiderivatives, or a large table of indefinite integrals, there were two conspicuously missing motherfuckers there. We had the integrals of sine and cosine. We had the integrals of secant squared and secant tangent, but we didn't have the integral of tangent. What the hell is the integral of tangent? And we also didn't have the integral of secant. Now that one turns out to be a bit of a doozy. So let's begin with the integral of tangent. This is one you're going to need to remember. I'll write it in terms of the variable theta. So let's evaluate the integral of tangent theta d theta. The reason we didn't put this on that table before is because we didn't have the tools at the time to show what it is. The necessary tool is u sub. Now we have u sub. So given what we've looked at so far, does anybody have a suggestion or an idea as to how we could find the integral of tangent?
Change it to sine over cosine.
Good, that's a good first step, right? It's really the only thing we can do. There's not much else that's going to jump out, at least not much that's natural. But tangent theta is definitely sine theta over cos theta. So our integral is now integral sine theta over cos theta d theta. And looking at this kind of through the lens of u substitution, what could we try?
U for cosine.
Yeah, very good. Sub for the bottom, right? Kind of, we like to sub for the difficult piece. We like to sub for the thing that we kind of want to have as a single expression. Subbing for the top here, subbing for sine won't help us. It'll actually, that substitution is very hard to make go through. But if you sub for the bottom, you know the derivative of cosine is sine. And since sine theta is upstairs here, it will cancel with the piece that we get from the differential. So we're going to sub u equals cos theta. And that means du is going to be the derivative of cos theta, which is negative sine theta d theta. Make sure you keep straight which one's, you know, integral, derivative, positive, negative. So here's my little substitution box. And if I plug in just for cos theta, I get here integral sine theta over u d theta. Now I need to get rid of all the theta stuff. First, I should get rid of the differential and then see if there's anything left over. Here, this will be nice. So if I solve this for d theta, I get du over negative sine theta is equal to d theta, which means this integral becomes integral sine theta over u times du over negative sine theta. Can cancel the sine thetas. There's also this factor of -1, which I'll move out front. And we get negative integral 1 over u du. And maybe you can see, thinking about what these steps would look like if we tried to sub for sine. What would go wrong, right? I would have u over cos theta, and then du over cos theta equals d theta. So I would end up with like cos squared downstairs, no cancellation. Instead of cancellation, the cosines would pile up. So this is really the way to do it. Couldn't get here subbing the other way. As done though, this is now an integral entirely in terms of the new variable u. What is the integral of 1 over u du? Or what is an antiderivative for 1 over u?
You have the ln.
Very good. Yeah, ln, absolute value. In this case, we would use the variable u because that's what we have here. So this is negative ln absolute value of u plus a constant. And the absolute values really do matter. Don't forget those. And again, because it's an indefinite integral, no bounds, the original problem asked about, you know, thetas. I can't give the answer in terms of u. I need to plug back in now. We only do this with indefinite integrals, but we must do it with them. Negative ln cos theta in absolute value plus c. So this is the integral of tangent theta, negative natural log of cos theta. And it's one that you need to remember. You need to add this to your table of known integrals or known antiderivatives. It is sort of a foundational thing. We just couldn't do it back in section 4.9 or in section 5.4 because we didn't know how to do u sub back then. And this requires u sub. We can't get there without it. Now, there is one more fun thing to talk about here. We know that the derivative of tangent, derivative, not integral, derivative of tangent is secant squared. And there's this Pythagorean connection between secant and tangent. Where you see a tangent, there is a secant nearby. So there's something kind of not super satisfying about saying the integral of tangent is ln cosine or negative ln cosine. And here again, we could rewrite the answer if you think about the rules for logarithms, the ln of the absolute value of cos theta is the same as the ln of the absolute value of parentheses cos theta all to the negative first power, right? This negative is a -1, and one of the rules for logarithms is that multiples out front can come inside as powers. Now, this isn't the arc cosine function. This isn't the inverse cosine function. This is actually an exponent. It's cosine of theta, all raised to the power of -1, which is 1 over cos theta. So here we have the natural log of the absolute value of 1 over the cos of theta. And 1 over cosine is secant. So this is the same as the natural log absolute value of secant theta. So when I said, when you see a tangent, there's a secant nearby, another way to write this answer is as the natural log absolute value of secant theta plus c. And this is actually how I prefer to think of it. So the integral of tangent is the natural log of secant, just kind of has a ring to it. Sounds nice. But you can remember it either way. Either one of these is fine, but you must commit this to memory. All right, just like you need to know your trig derivatives, you need to know your trig integrals. This is one of the foundational trig integrals. Got to know it. And you don't want to go through this every time. Obviously, it's not too hard, it's just a few lines. But committing this to memory, adding it to your table of known integrals, good move. Do it. So now we know how to integrate tangent. If I asked you to integrate cotangent, you'd do the same sort of thing. You'd write it as cosine theta over sine theta, and then substitute for the bottom, which there would be sine theta. And everything falls out very, very similarly. So you could add that to your table as well. The last kind of these 6 basic trig integrals that we just don't know how to do yet is the integral of secant, and this one's a real doozy. So let's talk about this. How do we integrate secant? In general, integrating odd powers of the secant function is hard. Integrating even powers of secant is not too bad, right? Like the integral of secant squared, we know that. That's just tangent. That's easy. But the integral of secant without the square, secant is just 1 over cosine. So it's not like the last one where we had sine over cosine and we could substitute for the bottom and the differential would cancel. If you wrote this as 1 over cosine and then tried to substitute u equals cos theta, you would end up with like still the du equals negative sine theta d theta, but there is no sine theta anywhere for that to cancel with. And so that would be quite hard. There's a trick here, and it's a weird trick. It's not a trick I expect anybody to come up with. But having seen it, I do expect you to be able to follow the argument. So here's the trick. Remember way back in chapter 2 when we were taking limits, sometimes you would need to multiply by the conjugate. Like you had to multiply by the square root of x plus 1 over the square root of x plus 1, that sort of thing. Here, we're going to do something very similar. We're going to multiply by 1 in a very clever fashion. We're going to multiply by this. Secant theta plus tangent theta over secant theta plus tangent theta, the value of this expression is 1. Multiplying by this does not change anything. but it does make it easier to see what to do. And it'll surprise you, I promise. So that's the trick. I don't know who came up with this. It was before Euler, but it was after Newton. So probably sometime in the 1600s. I'm not sure the first person to do it. And it's not something that we do for any other problem. So it's not like a method. It's not something you need to necessarily practice with, but you do need to remember the result here. We're going to figure out the integral of secant. You need to remember what that is. And I think the best way to remember that is to kind of go back through this argument we're about to do on your own. And the trick, again, to get started, you multiply by secant plus tangent over secant plus tangent. So what does that give me? That gives me, here I have secant theta times secant theta plus tangent theta over secant theta plus tangent theta d theta. Secant theta is the same as secant theta over 1. And fractions are always, right, top and bottom thought of as being in parentheses. This fraction bar is a grouping term. So now I'll multiply those fractions straight across, and I'll get secant theta times parentheses secant theta plus tangent theta all over 1 times secant theta plus tangent theta is just secant theta plus tangent theta. And the magic comes in the next step. I distribute this secant across this secant plus tangent. And then we're going to sit back and look at the thing until something jumps out at us. Secant times secant is secant squared theta. Secant times tangent is secant theta tangent theta. And downstairs is secant theta plus tangent theta. So this is my integral. So I want you to now stare at this with me for a second. What do you see here? Very good. The top is the derivative of secant and the derivative of tangent. The derivative of tangent is secant squared. The derivative of secant is secant tangent. The top, ladies and gentlemen, is the derivative of the bottom. Why is that useful? Because if we substitute for the bottom, the differential will cancel perfectly with the top. That's the beauty here. So we are going to sub, following Katie's observation, we're going to sub u equals secant theta plus tangent theta. Because that means du is going to be secant theta tangent theta plus secant squared theta all times d theta, which is the same as, I can change the order of addition in there, no problem, secant theta plus secant theta tangent theta d theta. So what do I get? I've got secant squared theta plus secant theta tangent theta all over u times, if I solve this for d theta, I get that d theta is equal to du over secant squared theta plus secant theta tangent theta. So that's what goes here. Du over secant squared theta plus secant theta tangent theta. And again, fractions, grouping symbols, parentheses, these cancel perfectly. There's a very clever individual who came up with this. I don't know who it was, but it's an incredibly clever argument. It's not at all obvious. It requires this weird trick. But at the end of this weird trick, we have the integral again of 1 over u du. And the integral of 1 over u du is still the natural log of the absolute value of u plus a constant, which is plugging back in because it's an indefinite integral, the natural log of the absolute value of secant theta plus tangent theta plus c. So there's two new things from today that you need to kind of add to your table of known antiderivatives. The integral of tangent is the natural log of secant, and the integral of secant is the natural log of secant plus tangent. I wouldn't make you go back through this argument on a test. It's not, because it's not something like, this is not a technique we use on other things. I don't think it's worth like drilling the technique, and it's certainly not worth testing this technique. But U-sub in general, you bet your ass is going to be on exam 3 and on the final and on your first test in Calc 2 and probably on your second test in Calc 2. It's going to be all over the place. It's very important. And you need to get comfy with the methods that we're using here. So the last thing I'll say here is just make sure you add these two known antiderivatives. Add to your table of integrals these last two that we did today. The integral of tangent theta d theta is the natural log absolute value of secant theta plus c, and the integral of secant theta d theta is the natural log of secant theta plus tangent theta plus c. We do use these quite a lot. These will show up as like parts of other problems where you have to do other stuff. They're just things you should know. Just like you know the integral of sine, you know the integral of cosine, you know the integral of x cubed. These are just things you should know. I'll make one last comment before I let you go, and that's that in general, integrals of odd powers of secant are jacked up. They're hard. This might seem strange, but it's the easiest of all of those. Even powers of secant, like I said, not hard. Integral of secant squared, you know. Integral of secant to the 4, I'll show you it's not hard. But integral of secant cubed, secant to the 5th, secant to the 7, those are quite tricky. And they reduce down to this. The way you do them is by running integration by parts and applying trig identities until you're able to get out some pieces and the integral of secant, which you then need to know is this. So these two are both quite foundational, especially when you get to section 7.2 in the textbook, which will be fairly early in Calc 2. You're doing lots and lots of trig integrals and then trig sum. All right, that's all I have for you guys today. On Friday, we're going to talk a little bit more about U-sub. I will show you kind of what I consider challenging U-sub problems. These are like middle of the road U-sub problems today. And then I'll also introduce our final section, which is section 6.1. And 6.1 is going to be when we actually do 6.1. I'll give a little introduction to it on Friday. But the proper lecture for 6.1 is, I think, our last bit of student teaching. So we want to make sure we're clear about the dates here. Let's do that. Our last bit of student teaching is going to be section 6.1, and we will be ready for that next Monday. So Monday the 12th, we will talk about areas between curves, and that's going to be Jacob, and was he working with someone else? Oh no, just you. All right. Is Jacob here right now? Ooh, he's not. All right, I will send him an email making sure he's got his materials together. But yeah, next Monday is going to be our last bit of student teaching. And then we'll be ready for exam 3. After exam 3, there's a few little topics I want to go back and talk about a bit more. We haven't really gotten to talk much about the mean value theorem. That's a beautiful theorem. We did touch on it, but I think a little bit more time talking about that is appropriate, and we'll review for the final. And then that's going to be it, guys. We're almost to the end. So make sure you're working on those honors projects. Make sure you have everything set up and ready to go. Yeah, so the estimated date for exam 3, already on U sub 6.1, review for exam 3. Exam 3, probably, we could do it next Friday, but I think it'd be better to do it like the Monday or Wednesday after. We're not crunched for time here. So yeah, we could do it a week from this Friday on the 16th. But I would prefer to do it, I think, on the 19th. I'll let you guys choose. Okay, I need to talk to my other Calc 1 class. I'd like to get those synced up. But we'll either do it next Friday or the following Monday. Alrighty, gang. That is it from me. If you want to talk more, you can come see me in office hours today. I've got an office hour from 1 to 2. Otherwise, I'll see everybody on Friday. Have a good day.